Hello, good morning and good evening, everybody. Welcome to the JSEET Keynote and Best Paper Award session. We will start with the Best Paper Award and then we will continue with the Keynote by David Garland. So regarding to the Best Paper Award, in this edition, the best paper for the JSEET goes to a paper titled Teaching Model-Based Requirements Engineering to Industry Professionals, an Experience Report. This paper has been published by Marian Down, Jennifer Brings, Marcel Goyer, Walter Cott, and Thorsten Weyer. Marian Down is here with us to receive this award. Hello, Marian, congratulations.
Hello, thank you very much. My co-authors cannot be here today, unfortunately. However, they and we are very honored to receive this award. And yes, thank you very much. And just let me take 1 minute to thank you two for the wonderful organization and all the work you are doing to make such a great JSEET experience.
Okay, thank you. Maybe we could give here a clap.
Yes,
congratulations.
Virtual applause for Marian. Congratulations, Marian. Okay.
Thank you.
Congratulations. Okay, so Hakan, the floor is yours.
Yes, I'm going to stop sharing my slide. And the next order of business is David's keynote. And David, I will ask you to actually share your screen and your slides in the meantime. And I will introduce you actually in a few minutes because the official start time is 10:40. So let's wait for that in case people may join a little later at the exact start time.
Okay, let me just check that you can hear me.
Yes, we can hear you. I'm going to also change the layout so that the main screen will be your screen share and the insert will be your camera. Okay, hopefully this worked. Can you hear me?
Yep.
All right, okay, good. Right, we'll wait for another 7 minutes. Let's do that just to be safe. Apologies to the audience because the official start time of the keynote is 10:40. It's best to wait in case people will join. So Anna, Marian, and myself, we're going to turn off our videos and mute ourselves once the keynote actually starts.
Mm-hmm.
Okay, Tim is saying, I don't think we should wait because all the other sessions are going, and people who join will be puzzled. Why don't I introduce David in the meantime? So welcome everyone to the keynote session. We'll just follow. We can't refuse Tim. We can't refuse Tim, so we'll have to just go on. Welcome to the keynote session. Today we have a guest who doesn't need really introduction. It's David Garland from Carnegie Mellon University. But I'm still going to tell a few words about David Garland in case you don't know a lot. So David is a professor of computer science, and he's also the associate dean for the master's program in the School of Computer Science at Carnegie Mellon. His research interests include software architecture, adaptive and autonomous systems, formal methods, and cyber-physical systems. Especially his work on software architecture is really well known and seminal. He is considered one of the founders of the field of software architecture, in particular formal representation and analysis of architectural designs. He has many awards in his pocket, including ACM SIGSOFT for significant and lasting software engineering research contribution, IEEE TCSE Distinguished Education Award, Nancy Mead Award for Excellence in Software Engineering Education. He is also a fellow of the IEEE and ACM. So let's welcome David Garland.
Thank you. Thank you. Let me make sure.
I think we're just going to go ahead and start it, David, based on the feedback from the participants.
Okay.
All right.
You can see my screen?
Yes,
Yes.
we can see it, and the floor is yours.
Okay. Terrific. Well, thank you, Hakan, for that nice introduction. And it's a pleasure to be here to be able to speak to all of you about my favorite topic, software architecture, particularly in the context of software engineering education. So it was nice to have a chance in putting this talk together to think about and reflect over the last 30 years of working in this area. And hopefully in this talk, I'll have something that introduces people who haven't been involved in software architecture education to the field, but maybe hopefully for some of you who have been, some new ideas that you might want to consider moving forward. Just a very quick elaboration of my history. I got my PhD at Carnegie Mellon and then went off to work in industry and found myself developing a product line with an architecture for oscilloscopes. At that time, architecture wasn't really a well understood field at all. And I decided I really wanted to go off and work on that. So I joined the faculty at Carnegie Mellon. I was fortunate enough to start working with Mary Shaw, who had been thinking in a similar way about architecture for a couple of years. We decided it was time to pull together materials, and we put together our first course in software architecture that we taught to professional master's students in software engineering. So this was the first time I think a course of this sort was offered. And over the next couple of years, we began to refine the materials for that, and that ended up with our publishing a book on software architecture perspectives on emerging discipline. The idea in that book was to try to get people familiar with some of the key ideas behind software architecture and differentiators between other aspects of software engineering, such as code development. At some point later, I was on sabbatical at the Software Engineering Institute and started a collaboration there with Paul Clements and others to write a book on documenting software architecture. And then later on became the director of the software engineering professional programs. And at this point, sort of moved out of that. And now I oversee all of the master's programs in the School of Computer Science. And there are about 20 of those specializing in everything from machine learning to robotics to software engineering to human-computer interaction. So I've been involved with software architecture for a long time at various levels. And in this talk, I want to share with you some of my insights and experiences, distill out, I think, some of the key things I've learned over this period. So the first part is really related to what should we be teaching? What does it even mean to teach software architecture? And I think we could summarize that in a word or a phrase: architecture thinking. What does it mean to think like an architect? The second part I want to talk about is, okay, once we know what we want to teach, or some of the things we want to teach, how do we actually go about doing that? And what are the challenges we have to overcome? What are the impediments to actually conveying the kind of ideas that we'd like to get across? And then finally, something that I've been pondering for the last few years is rethinking the scope of software architecture and software engineering education, perhaps extending beyond the normal notion of a course on software architecture to ways in which architecture thinking might infuse other sorts of courses and other kinds of education. So we'll start with what is architecture thinking. First of all, let's try to put it in context here. When we try to map out the great ideas in software engineering, broadly speaking, many of them that we might put on a timeline from the earliest days of programming up until today are about abstraction. They're about how do we manage the complexity of systems? How do we get our heads around systems of increasing complexity? How do we design them with the properties that we want them to have, and so on? And you can think of software architecture as one of the stepping stones in that progression of concepts. It emerged roughly in the mid-1990s as a kind of recognized area that people started looking at. And since then has been one of the foundation stones for many other of the innovations. So many systems today that we use or build on have some notion of architecture as its sort of backbone. And so architecture sort of stands in the middle here as an important step of developing some new abstractions that allow us to create systems of increasing complexity and diversity. So if we look a little more at the sort of evolution of the field, the idea of architecture has been around for a long time, almost, well, indeed, from the early NATO conference on software engineering in '68. And people have known that software has structure, and that good structure often leads to better systems. But for most of the history of software engineering and computer science, it's been a somewhat ad hoc enterprise. Now, there are some different interesting examples of architectural design that you see emerging in the early systems. For example, compilers often had a fairly regular structure that people could use to build systems or build compilers for particular languages. And even operating system design, although they might look somewhat ad hoc. Here's a hand drawing of the Multics system from MIT in 1972. When you look at it a little more closely, you discover it's actually a layered system. And so there's some implicit structures built into this. At some point, people began to think more clearly about how do we structure software, and in particular, trying to understand what's the nature of sort of composition at a high level, and how is that distinguished from what you might do as a programmer. And de Riemer and Kron made it respectable for researchers to talk about system configuration and system configuration languages. And other people, such as Dave Parnas, began making arguments for ways in which we might modularize systems to better enhance evolvability. In the 80s, we began to see papers and in general descriptions of systems talk about architecture, and these would come in many kinds of shapes and forms. So here are just a few snapshots of different kinds of architecture descriptions from various papers of the time. And you can see there's a lot of variability in these things. Some use lines, some don't. Different conventions for boxes and components, different levels of detail. And so what emerged from all of that was an interest in creating architecture as an engineering discipline, moving from ad hoc decisions and informal notions of what architecture design was to something that would allow practitioners to think about systems architecturally and design systems from an architecture level of abstraction. Instead of, for example, having the architecture emerge in some random way from the actual coding decisions. But in addition to sort of thinking about things architecturally, a renewed interest in building systems compositionally from parts, but also ensuring critical system requirements. So as systems are developed, the issues of functionality are often overshadowed by other concerns such as availability or security. Further, one of the things that we recognized early on was that good architects tend to reuse common patterns and styles. These are often used with sort of informal vocabulary, but nonetheless, they're a fundamental set of concepts that can be used as a starting point. In addition, beginning to reuse architecture design experience, for example, how do you solve problems about availability or performance by thinking architecturally? And from a business perspective, overall, how can we reduce costs of development using architecture, for example, to take advantage of commonalities as implemented in product lines or platforms and frameworks? So, again, going back to the evolution of the field, so what we saw was in the 1980s, before architecture was particularly well recognized, we had lots and lots of informal box and line diagrams, very ad hoc application of architectural expertise, and many projects didn't even have an architect. They might have a senior level designer, but typically architecture was not identified as one of the important aspects of the system design. As I said, in the 90s, we began to recognize that this information that would lead to solid design of systems could begin to become codified, and that there was a certain kind of expertise that people had that could do a good job of architecting systems. And so there was a recognition from industry that, well, maybe we should actually have job titles, for example, of architects or training programs for architects. Along with the notion of architecture also came the notion of integration of architecture with everything else. You know, how do you fit it into your overall design processes or development processes? How do you document architecture? There was also an emergence of a lot of interest in product lines and commercial and standard, government standards. Various component integration frameworks began to emerge. And we began to see some of the vocabulary being written down with notations and tools for actually representing architectures directly. And finally, books and courses on architecture. So this is when Mary and I, for example, were developing our first course in software architecture, but others also were looking at this and started publishing books on the topic. So in the 2000s, what we saw was architecture notions begin to find their way much more into the mainstream models, notations, processes. So we end up, for example, with UML2 taking particular concern for architecture modeling, various sorts of methods that were proposed for developing systems using architecture as one of the important parts of it. Some architecture analysis tools, mostly domain specific, and some standards largely for enterprise systems, but with a strong architectural notion in them. In the 2010s up until now, we, of course, have major shifts in technology. So the emergence of the internet, various sorts of platforms, frameworks, and ecosystems that people now build software routinely to fit into. The emergence of cyber-physical systems that causes software engineers to think much more about the physical world in which they operate. Concerns with how do we integrate architecture into modern software development processes, in particular agile processes, and some of the concepts that have emerged that are fashionable in industry, but if you're not careful, may leave architecture out in the cold because they don't pay attention to that. And more recently, incorporation of AI into systems and the implications for architecture on that. And if we look around, what we see are there are a lot of resources for a software architect, from training and certification to books on standard architecture patterns to lifecycle models that incorporate architecture, evaluation and validation methods, documentation approaches, commercial grade architecture infrastructure, career tracks, journals and conferences. So all the trappings of a fairly mature area. Which leads us to the question, what should we teach? And how should we go about teaching it? So that's what I want to focus on now. We have this large body of knowledge, techniques, application areas, methods, quality concerns, and in vogue technologies, things people are using on the street. And the question is, well, given all of that, perhaps too much knowledge, too much information, how do we distill it down into some fundamental principles and skills that we can identify as being sort of the core of the field that we could try to teach to aspiring architects. So I want to go through what I think are 5 or 6 big ideas or key ideas in architecture that I think, in my experience, are the heart and soul of architecture and the kinds of things that we should be teaching or trying to get people to understand when they learn about architecture. So I'm going to go through all of these somewhat quickly, but and at a fairly high level of abstraction, but hopefully communicate sort of what the big ideas are. So the first one is, how does architecture fit into the broad view of software engineering as a whole? We have requirements, typically, maybe not fairly well formed. We have implementations. How do we relate those, or how do we bridge the gaps so that the implementations that we create match the requirements that we have? And in a somewhat undisciplined world, we might say, well, we just throw a bunch of programmers at the problem and they hack away, code away, and then hopefully in the end of that, we have an implementation. And a lot of processes work this way, or a lot of development projects work this way. And to some extent it works, but it tends to be ad hoc. It's somewhat unpredictable, can be very costly if you discover later on that your implementation is missing some important property, let's say some performance bottleneck exists in the system that you hadn't anticipated. So we'd like to do better, and this, of course, is why software engineering is what it is. Architecture says, let's think about this by imagining a somewhat 2-step process. Instead of going straight from requirements to implementation, let's think carefully about a high-level system design in which we grapple with the hard requirements of a system and build our design in such a way that we have more confidence later on when we implement it that the important qualities of the system will be embodied in the implementation. So architecture is somewhat of a bridge here then between requirements and implementations, Obviously, it isn't as detailed as an implementation, but it is in the solution space and is an attempt to make sure that the top-level qualities and functions of the system are in the system. Okay, so that's number one, is a bridge. Architecture is a bridge. The second one is, I like to say, software architecture puts the engineering in software engineering. And what I mean by that is when we think about what is engineering, it's typically about making a system that balances a set of often conflicting requirements, where you can't have everything you want and where there's kind of a mutual dependence between various properties of a system that requires some deep thinking about design choices. An example that I like to use in my course goes back to the Google file system architecture that was published quite some time ago, but has some interesting properties. This is an informal diagram, but if you try to understand this diagram as to why it is the way it is, it's an interesting intellectual exercise. So this is the back-end system of Google, which has to manage a very large number of documents and deal with failures and performance issues. So in order to understand this, you first have to think about, well, what are the qualities of the system that we care about? And these are at least four of them that emerge if you think about this. The system must scale, it must be reliable, it must have reasonable performance, and the cost of the system should not be too high. So if you approach the problem with those qualities in mind, very quickly you discover that many of these things are in opposition. So scalability in this case is handled through horizontal scaling, where you can add more servers and more disks to accommodate larger amounts of data. But then to deal with cost, you have to decide, are we going to do high-end or low-end deployments here? Google decided to do low-end, and that induced a reliability problem, which is then solved with this component here that attempts to discover which parts of the system are working and which ones aren't, and then self-adapt itself to recover from various kinds of faults. And this becomes the sort of central point at which applications can find documents, which then introduces a new problem of a potential bottleneck, and then requires you to think very carefully about the connectors. So as you work through this, you see that the driving forces of this design are not the functional requirements. Far from it. The functional requirements are actually incredibly simple. You have to be able to store and retrieve documents. The hard problems all come from these ilities, or the quality attributes, scalability, reliability, performance, cost, and so on, that are often difficult to get right. And so architecture is really thinking like an engineer about these qualities and the trade-offs. The next major idea that I think has sort of set the field on a reasonable foundation is this idea of common idioms, platforms, patterns. And this is an interesting area, but one thing that's helpful, I think, is to recognize that the kinds of styles and patterns fit within a spectrum of choices. And at this end of the spectrum, or this end of the space, what we have are very, very generic kinds of styles, notions of data flow or call return, asynchronous events. As we start to move towards more specialized things, we end up with architecture designs that are more constrained, but give more power in the sense there's often code that you can reuse, analyses you can reuse, and more kinds of assurance that you get by using those particular styles. And we can continue to move here towards more domain-specific forms of architecture, all the way over to product lines where we have things, architectures that are specialized to a particular company and a particular set of products within that company. So understanding this space is an important part of architecture thinking. The fourth idea is this idea that these styles, you might wonder, don't they go out of fashion, or don't they eventually end up being obsolete? And my experience is they don't. They morph over time, and hence it's really important to think about these things as sort of fundamental computational metaphors that are likely to exist forever, even though how they're manifested in technology is quite different. So I'll give you a very quick example of this. A data flow system is a system that processes data by receiving it in the inputs and then transforming that information by having components that read data in through their input ports and write data to their output parts and communicate to other components downstream through some kind of data channel. So we have, in the very earliest days of computing in the 50s and 60s, we have a form of this that we call batch sequential, in which companies would do various kinds of business level processing by having data on magnetic tape, reading it into a program, transforming it, writing it out to tape, and doing that successfully until eventually you get something out the other end, like a report. But we also see this in the form of compilers, where there's sort of a standard flow of data from an input to the output. Later on, as technology matured, we began to get the possibility of concurrent and multiprocessing. And so this emerged in a style refinement called pipes and filters. And so in this world, instead of sequentially transforming all the data, we can kind of pipeline the data through the system, where the components are reading essentially a stream of data and writing to some kind of communication mechanism that buffers the data and allows some asynchrony among the components, so that you get the latency of outputs is much shorter, because now you're doing concurrent processing. And we see this in a variety of forms, but sensor processing is one example. As technology matures and we begin to move into clients and servers, we can see the same paradigm occurring again. So here in Apache, both the input and the output processing parts of the Apache web server are essentially pipe filter systems, where you can add your own filters in the input or the output processing. Moving beyond that to more like today, what we see is a form of this in things like cloud-based AI pipelines, where we're pushing data through a sequence of transformations in order to train some model, for example, for classifying images. And finally, fully internet scale systems, compositional systems, where you can put together a pipe and filter system or a data flow system using off-the-shelf components that are stored on someone else's server and simply plug together through a web browser to get a new system very, very quickly and in a very powerful way. This is an example of a Yahoo pipe, which has now been taken over by another organization. But for example, a composition of this sort might be put together in order to search for apartments in your local area by consuming things like Craigslist and putting out as an output a map that shows the location of available apartments within some price range. So what we see here is this idea of data flow starts out in a very primitive way because of the technology, and now scales up to internet scale. And we see this not just with data flow, but all the other major forms of architectural styles. The final point, next to the final point is has to do with what I think is one of the defining characteristics of architecture as distinguished from programming, and that is the connectors. When we put systems together, we often focus on the boxes. What's the computation that's happening? But most of the action, or much of the action that affects the qualities of the system, really relates to the ways in which things communicate. So, for example, if we have two filters, we might communicate through a pipe here. Now, why do I say they're important? Well, of course, we want to draw the lines, but more than that, I think we really need to focus on what are the semantics of these connectors. They're not just lines, they actually represent some kind of semantic glue that makes the computations work together. So, for example, even in this simple case, there are lots and lots of detailed questions that this would need to get answered in order to understand this. For example, well, which direction is the data flowing? Can F2, what happens if F2 tries to read from this pipe and it's empty? Can F1 choose to stop writing? Can F2 choose to stop reading without consuming all the data? What happens if F1 can stop writing, closes the pipe? Could it start up again? What happens if F2 never reads and F1 continues to write? Will it be able to write indefinitely? So these are all semantically rich questions that require us to think about things like pipes as first-class design entities when we're building systems. This is not true in programming languages. In programming languages, the kind of connective glue that we have, which are procedure calls, shared data, and so on, those tend to be wired into the programming language. Here we have our own ability to define the kind of connectors and communication mechanisms. Lest you think that that's a kind of silly example, one of the systems I worked on for a while was the HLA distributed software, distributed simulation environment, which was a fairly sophisticated standard for combining multi-vendor simulations that the Department of Defense sponsored, and then later became an IEEE standard. Okay, the final point I want to make is the notion of perspectives and views. In the early days of architecture, there were a lot of arguments about, well, what is architecture? Is it about code structure? Is it about physical layout? Is it about runtime structures? And today, we've matured so that we can understand that architecture actually involves different kinds of information that has different value in terms of representation. So, for example, we may need to talk about the structure of the code in order to reason about maintainability. But if we're going to reason about performance or availability, chances are we need a runtime perspective so we can reason about things like what's the sort of redundancy in our system. But also, if we're thinking about performance, it's very likely we need to understand our physical infrastructure that we're deploying this on. So modern software architecture tends to try to be very careful about what sorts of information are represented and how. Okay, so that's part one. What is architecture thinking? And I've listed 6 major ideas here that I think are fundamental to architecture. So let's look at educating software architects. I just want to first of all mention what I think are some of the challenges, the ones I've run into that I think you need to be aware of as you're thinking through how do we go about teaching architecture. The first is that students who come to these courses that you might teach or training sessions in industry are often very good programmers, but they don't know how to think at the system level. They tend to focus on particular features, on correctness of the code, perhaps data structures and algorithms, but they have very little experience with thinking at the systems level. And as a result, when they're given a problem to solve, they often dig into the details much too early without thinking about the broader qualities of the system that they need to think through. They often come to these courses also or in some cases without a lot of systems development background. So the notion that performance, availability, security are key properties that you need to design into the system is somewhat foreign to them. And often we'll think, well, I can just add that on later, and not recognize that that's extremely difficult to do in many cases. And finally, today's marketplace provides some disincentives for students to learn about architecture. Most companies that are hiring software engineers are looking for good programmers. They're not going to hire an architect for an entry-level job. Or they may be okay with having architecture in their background, but that's not going to be what causes them to actually hire them. And in fact, architecture had a bit of a bad reputation recently, because people will talk about so-called architecture astronauts. These are architects who don't know how to actually implement anything, but they're off in the clouds thinking about things at this level of abstraction that isn't actually practical. There's also, I think, as educators, there are a bunch of challenges. So part of it is when you focus on architecture, you really also need to think about where do the requirements come from, and what should they look like, and how do we make sure the implementations that are produced to implement an architecture actually satisfy the architecture. So it's an end-to-end perspective that we need to consider, not just architecture. A second problem is, how do we connect to other software engineering courses? So often it's taught in isolation, but there are key overlaps in things such as requirements or system analysis. And indeed, many programs in software engineering have some kind of capstone project in them. Often students are not held accountable to actually do architecture design in those projects. And so there's a missed opportunity for covering that. Finding the right size case studies, I think, is another problem. You want them to be big enough that they're challenging, but if they're too big, then you can't do it in a single course. And finally, there's a tension between principles and techniques. I've talked about 6 main principles, but there are a lot of techniques too. If I want to improve availability, how do I use redundancy, for example, effectively? Similarly with security and so on. So we need to find the right balance there. So I'm including here a slide with a snapshot of a curriculum in the course that we teach as of a couple of years ago, just so you get some idea of what sorts of concepts we have. But what you can see here is from a major topic point of view, we talk in general about structures and properties. We talk about styles and patterns, so they have the vocabulary to think about system design. And then we teach techniques and methods, including requirements, analysis, documentation. And then we spend a big part of the course looking at architecture for X, where X may be performance, availability, security, and so on. So we focus in on specific techniques for that. And then finally, we try to expose students to some of the emerging trends and potential that's coming down the road that they might want to be interested in. If I look behind the scenes here, I think the thing that we try to do is to balance principles and techniques by teaching both, and in particular having architecture for various kinds of qualities as specific focus points. With respect to projects and right sizing of those, we have a mixture. So we have short exercises that you can do in an hour and a half with students just on pen and paper, on weekly recitations. We have 4 two-week team-based projects, and then there's a final project, also team-based, but that's directly linked to their capstone project, where they get early review by the instructor and they have to make a final presentation. So trying to balance out short and long. One of the key aspects is we try to bring in guest lecturers from industry, particularly in the architecture for X. So we try to find, for example, a security architect who can come in and say, how do they think about security? And then we try to form explicit linkages to other courses. As an example of a simple exercise, here's one that we use where we say, imagine you have this standard sort of 3-tier kind of architecture. Where do you put input validation? In order to come up with a reasonable answer, and there are many possible, the students have to think, well, what do I care about? What about security? What about performance? What about usability? And so on. And depending on how they think about that will cause them to put various kinds of input validation in various places in this architecture. And getting them to think that through and then argue for their own choices is a very useful exercise that you can do in an hour and a half. All right, moving on now to the final part. What I've said so far are things that I probably would have said in a lecture or a keynote of this sort 5 or 10 years ago. But I've been doing some thinking over the last few years, in part to deal with this problem that a lot of students who go into industry find themselves often confronting architecture problems and not having the techniques to deal with it. So I wanted to pose a challenge here for all of us in terms of how we might rethink the role of software architecture and its scope. So let's go back to this picture that I showed earlier of software architecture as a bridge. Well, in that world, we tend to think of training the architect. The architect, or maybe there are a couple of them, are thinking through the architecture carefully, maybe talking to people in the requirements world or development world, but they're kind of in charge. And I'm increasingly feeling this is not the right way to look at it, or at least it's certainly not the whole story. What instead? Well, when we think about architecture today, you don't have an empty box that you fill up. What you have typically is a context in which many of the frameworks, the platforms, the base of code and infrastructure is such that you have a starting point that's already made many commitments to an architecture. And then what you get to do as an architect is you get to plug in the pieces that are relevant to your particular application. Well, this changes things quite a bit because now we have to think about the investment in the infrastructure, the platforms, the reusable parts. And that may involve the product manager thinking across many products. It may involve the framework designer who's has to come up with frameworks that can be reusable. It may be a framework integrator that's attempting to bring in several frameworks from various places. It may involve programmers who have to know how to use the frameworks and what the architectural implications or constraints are that come with them. And you may even have end users who get involved in the process here, and I'll say more about that in a minute. So what this means is the population of people that need to know something about architecture is really quite large. And so the question is, well, how do you deal with them? Is it the same kind of education? Are there things that they should know? And how do you tailor software architecture to these people? So a couple ideas here. I'm going to go through them fairly quickly, but I think we can think about architecture for programmers, people who are not going to be architects in the traditional sense, but may need to make architecture choices as they code. Architectures for end users and architectures for managers. So architecture for programmers, I was kind of giving this a short name, architecture in the small. And the point here is that programmers often end up having to make architectural decisions, and they just don't realize that they're doing it. There are many examples where this occurs. For example, you may have an architecture that specifies the system will be layered, but programmers routinely break the layering by making a call around the layers in order to improve performance. Well, that's fundamentally an architecture trade-off that you're making of performance versus modifiability. But it occurs in many other situations too. And I think if we start to identify these and say, look, these are contexts in which programmers are going to run into decisions they have to make, which have architecture implications. A good example is when you're trying to make two components work together, maybe they don't work together out of the box. So what do? Well, in many cases today, you throw a junior programmer at them and say, well, hack it together so it works, not realizing that there's a whole range of principled ways or alternatives that you might pick to make them work together. I don't have time to go into these in detail, but once you know that there are lots of principled techniques, then you can think more clearly about which one to use in a particular context. Or similarly, availability. One of the problems is how do we improve availability? And once you've studied this area a little bit, you realize that there are lots of ways you can do that. For example, if you want to monitor a system, there are a number of techniques, from things like heartbeats or ping echo or recognizing exceptions that you actually have a choice about. So as a programmer, don't just pick the first thing that comes to mind or what you did last week. Think about it carefully. So I'm going to skip over this. Another area where I think architecture training can be very helpful is for end users. So when we look around, we see the actual end users who are building and using systems is much, much larger than the actual real trained software engineers. And they are in a position of composing systems, often at an architecture level, but they don't have good ways of thinking about how do I talk about the qualities of the system or analyzing them. How do we know how long the computation will run? What about privacy risks and so on? And there are many of these domains where we see essentially architecture design environments for end users. But those end users don't have the ways of thinking architecturally about their system. So they tend to hack things together and experiment and tinker until they get something that works, but nothing principled. So many of these are bundled up in very sophisticated front-end environments. Here's 4 examples of them that we've looked at. And so providing good architecture concepts for this very large set of people is important. Finally, for managers, I think one of the things that you have to deal with is how do you give them the right intellectual tools to decide how much architecture to do and when to do it, and also the implications of architecture on a much broader world of ecosystems. And in this context, I think it's really important to help counter the current trend where when you think about what you might do in an agile process in terms of addressing a backlog, you often have a choice between dealing with visible changes, so adding functionality, which provides positive value, or fixing defects, which reduces the negative value. But there's another dimension here of the invisible things that you need to balance out in your portfolio of effort. So as a manager thinks about, well, do I throw my programmers at refactoring and thinking about architecture, or do I have them add the greatest new feature? They need a framework within which to reason about the positive value of actually working on the invisible things. So let me conclude here. Software architecture has come a long way over the past few decades. It can be taught effectively, but I think we need to recognize that there's some inherent challenges in doing that, some of which I've listed here. But I also think there's a lot of potential to broaden the scope of who we teach, to find ways to bring architecture concepts to programmers, to end user architects, to managers, and to many others, who find themselves in a position where they are going to confront architectural concerns. And it's kind of up to us to help give them the techniques, the ideas, the concepts, the skills to do that. Let me just finish by thanking many, many people who I've worked with over these years. Mary Shaw, Tony Latanzi, Bradley Schmerl, George Fairbanks, Michael Keeling, Paul Clements, among them. They've been really colleagues in the true sense of the word, in terms of really trying to figure out what is software architecture and what can we teach. So with that, I will stop, turn it back to Hakan. If you have questions you'd like to ask, I'd be happy to answer them.
Thank you very much, David. We have already a couple of questions on the chat window. Let's give it up for David first. Virtual applause. Thank you, David, for the wonderful talk. So first question comes from Neil. And Neil is wondering whether CMU found a big difference from the undergrad courses to the professional master's students, who presumably have more experience in terms of how they handle or absorb architectural concepts.
So what was the start of the question?
So let me read it just verbatim. I was wondering if CMU found a big difference from the undergrad courses to the professional master's students, who presumably have more experience.
Indeed. Of course, yes. So, if a student doesn't have experience, from his experience, you have to, I think, approach this differently. And in our courses at CMU, the undergraduate software engineering tends to approach it by working up from the programming level through notions of frameworks and patterns and composition at the code level, moving towards increasing levels of abstraction. So approaching it from that level. For a more mature person, I think you can start at the top and say, look, we have a system with a set of requirements and qualities that we care about. Let's design our system to have those. But you have to get an undergraduate to recognize all of a sudden that, not all of a sudden, but over time, that making choices in terms of how they use a framework or where they position their code, let's say on the client side or the server side, is going to have an impact on performance. So they have to be brought up to that level.
We have a question from Jonathan, and he is wondering, when the choice was made to have 4 two-week team-based projects in your course, what was the former model? And would you consider this to be the model that has had the best impact?
Well, we've always believed that you have to do it in order to learn it. So we've always had some number of projects, but the nature of the projects has changed over the years. So I'm just saying a little bit more about that. Of the 4 projects, the first one mainly focuses on requirements. How do we actually figure out what quality attributes the system must have and document or write those down in a way that are actionable, so that once we've done our design, we can go back and say, have we met those or not? The second one is much more implementation oriented, where students have to start with an existing system in an architecture and then extend it in order to understand that certain kinds of architectures are extensible in certain ways and not in others very easily. And they have to take it all the way down to implementation, so the system actually runs. The third one we've used typically has students looking at someone else's architecture. So there's a book on a multi-volume book on architectures, or they can find another one, and they go off and they try to understand someone else's architecture and critique it. And the final one is often a documentation exercise where they try to take a system, often their own, and improve the documentation on it so that it's actually clear what's going on. So the projects are all quite different. Some are much oriented towards the hands-on architecting process. Others are more oriented towards consuming architecture or critiquing others. And yes, I think we're happy with that. The only question and issue that's really come up in the last couple of years is we've moved in the software engineering professional programs to a half semester refactoring of the program, so that each semester course is now divided into two. And this has had an interesting opportunity for us, because what we do now is in the first half semester, we teach general principles and ideas about architecture, and then students go off in different directions. So the people who are interested in embedded systems will do one course on top of that that deals with architectures for cyber physical systems. And then there's sort of an enterprise group that goes off and looks more at sort of IT-based advanced architecture. So that turns out to be a useful way to decompose things.
We have a question from Gregor, and Gregor is asking about architectural frameworks. You didn't mention the whole field of architectural frameworks, which start at business architecture and go down to infrastructure architecture. Is it not easier to teach software architecture when this topic is embedded into the whole life cycle?
Well, clearly, architecture does need to be embedded in the life cycle. The question is, how much time do you devote to the part around it? So if you think of it as a sandwich, where architecture is the part in the middle, let's say the meat or the cheese, and the bread are the other business-oriented and sort of developmental sides of it, you need to strike a balance. So certainly we spend a lot of time, and I think it's really critical to understand that the quality attribute requirements of a system are fundamentally traceable to the business context. You know, how much performance do I need in order to retain the customers of my web service? What's our availability or security requirements as sort of coming down from the top? On the other hand, I think, it's often a mistake to go off too much into business process architecting. There's a whole separate field of enterprise architects where you're trying to architect the overall, flows of information in a business context. And while that's useful to learn, I think that takes away too much from the more technical side of actually doing architecture, of making engineering choices.
Sridhar is asking about open source. Most of the open source repositories do not have architecture artifacts on GitHub, but still might work. And the question is, how can we say that architecture is a critical thing in an open source environment?
Yeah, it's a great question, and one that we struggle with. I think this is one of the problems for open source repositories. But one of the things, well, for example, we're working with ROS, the robotic operating system, a lot these days, and that's a very, very large open source ecosystem. Although they don't have architecture descriptions, you'll have something called a launch file, which essentially determines the sort of runtime configuration of the system when you start it up. And so we've actually been developing tools to extract out an architecture description from launch files and static code analysis. I think, many open source systems have these architectures as a kind of implicit notion behind them. And unfortunately, the knowledge about those architectures, the constraints that are embodied in them, they live in chat sessions and online blogs and things like that there isn't a good centralized place for that. And I think that's unfortunate, because people end up discovering, oh, by the way, this API can only be used in certain kinds of ways because of some constraints that are placed on it, and we didn't know that when we first used it, and now we're stuck. That kind of thing, I think, is a problem. So I would hope over time that the kind of architectural commitments of embodied behind open source systems are more explicit. The books, by the way, that I mentioned are called, I think, The Architecture of Open Source Systems, and it's a 2 or 3 volume set of people who have developed open source systems talking about their architecture. So it's a good source, actually, if you want to go and find examples of open source systems where someone is at least trying to explain the architecture.
Question from Jose. The sample syllabus looks great and comprehensive, but I worry that more hands-on experience might be required to meet certain goals. For example, employability. Is this intended to set apart the roles of architect and developer?
Let's see. I'm not sure what the core of that question is. I guess one of the things we do face is, when students go for interviews and are trying to get a job, they're often faced with questions, develop a coding solution to problem X. And they don't get in the door unless they can answer those kinds of questions. And so we do have ways of focusing on that and making sure they have that kind of background. But I think what's important is that the second interview, students are often challenged with much more systematic and systemic kinds of issues. How would you configure this distributed system to support the kind of reliability requirements that we have? And for that, architecture becomes really critical. So I think finding challenge problems of that sort, where students are forced to think on their feet about making trade-offs and various design choices they might make in a broader system context, is still useful, even if the sort of initial kinds of job interviews or even job roles that they're hired for don't focus on that.
Is the syllabus explicitly trying to distinguish between the roles of an architect and a developer?
Well, that's a really good question. And a lot of companies think you shouldn't be an architect unless you're also a developer. And I think there's some value in that. My friends at Google, for example, they don't distinguish architects as much. Because everyone is sort of involved in implementation. I think that keeps architects honest. You avoid the architect astronaut syndrome. On the other hand, it does take away from the time people have to think, more broadly about systems and about the evolution of systems over time. So I think there are real trade-offs there. I don't think you need to have a hard distinction. And in fact, in the course we teach, you actually have to build systems with your architecture. You can't just design it and call it a day. You have to understand, okay, well, how are we actually going to implement this system? And in order to achieve the things we think. And sometimes that involves going back to the architecture when you realize, oh, we can't do that with the infrastructure we have to work with. I can't, guarantee for example, the sequential delivery of messages in my system. So now I have to think about that architecturally. So I think implementing and architecting do have to go hand in hand, at least in terms of learning architecture.
Yes, and Patricia on the chat window is echoing that sentiment, David. She's saying that she thinks it's important in a software architecture course to explain explicitly that architecting is a role and not a person. I think this is in line with what you have just said.
Mm-hmm.
Okay, so we have 40 seconds left before the session closes. And
by the way, let me just throw in one last thing, because
sure.
I didn't put this on my slides, but it just occurred to me. There's an interesting development around this idea of architecture design records, or ADRs. And if you look that up, architecture design record, this is a way to broaden the participation in architecture to a whole team, where architecture decisions are made more collectively, but still documented and still thought through at an architecture level, but basically spread the rollout over the development team. I think that